Sì. Sincronchi. Bazzichini. Oh. Sembra Так, ладно. Ну, бенз. Students. Time to do something. Okay. What's for today? I would like to take a closer look on discrete time processing limitations. Now we have what we have? Table of signal. After we performed analog to digital conversion, we have table of signal values. Yeah? Yeah. But it's not so easy. There are, how to say, underwater stones in all this. Before we speak on precision and, how to say, adequacy of our date, I need one idea. I started to talk about adequacy of discrete time representation of signal. So I need one idea. Let's see, one basics. Whoa. I found you. I thought it's lost, but he is. Good. here I started to talk about adequacy of discrete time signal representation. Before I'll speak, I need one idea. One idea. Let's say something like this. This is time. I need one signal. I can name it delta from time minus tau by half, and its magnitude is 1 divided by tau. A rectangular signal, delta from time. It's here, 0 point. So equals to 0 if time is before minus tau by half, 1 minus tau by half, 0 tau by half, and again 0 if time is greater than tau by half. Such kind of pulse. Nice. If we calculate area, how can we calculate its area? Integrate it. Yeah. Yeah. So area of the signal will be equal to minus tau by half. 1 divided by tau, 1 unit. It's always an area of unity. Now, let's take a look on one thing. Let's say I have some kind of voltage being a time function. And here is my T0. This point is T0 minus tau. T0 plus tau by half, and here of course tau by half. Let's take a look on integral of multiplication. Let's take a look on something like infinity to infinity, delta shifted by T0. What will we see?
This 50 minutes and you get the class. Yesterday also we finished the class 30 minutes, right? We left out
Done. Okay. What we will get? We will get T0 take it, let's take del 0 delta. Let it be in this way. Unclear, why should I need this? You'll see. In theoretical world of my blackboard, I can select tau so short what? Look at this point. T0 minus tau by half. This point is what? It is 0 plus tau by half. So take a look. I can always select tau so small what? 0 minus tau by half will be near equal tau by half. Something familiar, né? Something close? You started ADC conversion at point minus, you ended ADC conversion at point. So there always, in theory, I can always find ADC so fast that conversion time can be, how to say, omitted, because voltage will not change within conversion period significantly. So this means what I can substitute approximately my integral with voltage at point 0 integral T0 minus tau by half T0 plus tau, tau by half T0 or it's approximately equal to voltage at point T0. What I wrote? One sample of fast ADC. In word of mass, taking a sample, taking a one measurement, equals to multiplication with this rectangular, how to say, selector window. Because this is true for any time moment. Okay, our ADC is operation. This is true for any time moment. I can I can collect all samples together. Because I use time, I will use x as an integration variable. So I can substitute my voltage with minus infinity to infinity delta x. Sorry, maintenance time. Dx, or it's approximately, I can do it in opposite way. terms of mass. What I can represent my voltage as a set of tau-like narrow strips. Tau-like, not like, very thin narrow strips. One, going one by one. But there is, how to say, kind of uncertainty. What means short enough? It's kind of uncertainty. In mass world, we can go to the limit. Let's introduce delta function. Something familiar? You had electronics course, no? Delta function. Infinitely thin. Oh, it's like needle. If this is point 0, delta from 0 equals infinity, and delta for any time not equal to 0 is 0. Absolutely thin needle. Time delta function minus p 0 equals to, this is the 0, and it's fly up to infinity. It goes up to infinity. Fastest thing in this world is a delta function. If you integrate delta function in infinity, imagine, not important, you will always get unit. In case of real delta function, real, true delta function, infinity to infinity, delta function is 0. The time equals to at that 0. What does this mean? It's absolute ideal sampling. Ideal ADC performs its operation instantly, without any delay, and gets us absolute precise value of measured signal at point t0. We gave command do it, and absolute ideal ADC performs for us measurements with absolute precision, instantly. Absolute, or I'm missing something? We have two uncertainties. Remember, when we speak on analog to digital conversion, we have two errors. Errors by time and errors by magnitude. Our time was like this. We will get, I don't know, something like this, where this is timing between sampling or discretization period, but here, maybe I draw it in orange, will be difference, and max of this difference is E0 reference voltage divided by 2 power n minus 1. If we connect, then we will get some kind of, instead of smooth wave, we will get something like this. It's if we connect dots. Maximum step between measurements in vertical, in magnitude, is how to say, ability of ADC. It's our resolution for n or the ADC. It's double 2 power n minus 1, not double but 2 power n. In case of plus here, for ideal IDC, this one corresponds to ideal IDC taking samples instantly. Not ideal IDC takes some time for performance operation. Even with sample hold device. Sample hold also not works instantly. It needs some time, there will be some transient, it needs some time to charge its capacitor. Even sample hold not works instantly. In real life, there will be some time uncertainty. This is ultimate point, absolutely fast ADC. Okay. I can write infinity to infinity. The x or equals minus infinity to infinity x del minus x dx. What I wrote just, if you have absolutely fast ADC with zero time between sampling, there will be absolutely no distortion. Result of conversion will be original signal without any distortion. Appears useless. What means absolutely fast ADC with zero sampling time? This means what? I can, because this is ultimate limit, endpoint. This means what I can achieve any precision with adequate sampling frequency. If at the end of the row is absolute precision, I can achieve any precision from no precision to absolute with adequate sampling rate and of course conversion time. This thing is important. It tells what any precision is possible. One more thing. I can tell from minus infinity to time. Okay. Let's simplify. Equals to from 0 to infinity and equals 1/2. So integrating from minus infinity to time the 0 yields 0 and time is before the 0, 1/2 and time is equals to the 0, and 1 and 1 when time is greater than 0. On the basis of this, it's easy to understand one thing. One. The 0. Something familiar? Huh? Switch on function. 1 from time. You have your course in electronics. Familiar thing? Switch on function. It appears in Laplacian transform or Carson Heaviside. What did you have? Laplace or Carson Heaviside? Laplace, or Laplace. Okay, so 1, 0 is better write this delta 0 by time. Delta function is a derivative of switch on function. I don't know. If you know Laplacian transform, you should know also about spectral function. What is spectral function? Before Laplace, how did we get Laplacian transform? When it appears, how? What's the basis for Laplacian transform? Eh? We had Laplacian transform in our course. So, what was before? What? Fourier transform of non-periodic function. When you try Fourier transform for function not confirming with the Dirichlet conditions, you get nothing. To get something, what you do? You multiply your original with a power minus ct, or in different notation, a power minus sigma t. There is no difference. So you will get Fourier Laplacian transform is Fourier transform from your signal multiplied by a power ct, where c is constant. As a result, you get spectral function of complex frequency. P or S, no difference. P being C plus J omega, S being sigma plus J omega, but it's the same, it's only different notation. Spectral function is Fourier representation. Take C 0 in Laplacian transform and you will get spectral function. Complex function of frequency. Since area of the pulse, we started with it, is unity. Infinity started from minus 0. Sorry. A power minus omega, I'm the time, equals to 1 a power of omega t 0. In case we performing Fourier transform on delta function without offset yields us 1. This function has a uniform spectrum 1 on any frequency. Inverse transform of delta function, you can write this way: 1 divided by double t minus infinity to infinity spectral function of my delta function a power omega. The omega equals to 1 divided by double t plus infinity to infinity a power of omega term the omega. Okay, I need one extension of delta function. So multiplication. If you multiply something by delta function, it's like taking absolute precise, absolute fast sample. More. More about. More. What's more? One. More. One moment. Okay, let's cosine omega 0 time plus chi phi 0. Ideal voltage. It's cosine because it's radial voltage. Okay. I can perform Fourier transform on it. Can I? Oh, if I knew Laplacian transform, I knew also Fourier transform. Can I perform Fourier transform? Can. Frequency representation of this signal will be what? I need Fourier transform to infinity O max cosine omega 0 time plus phi 0 f power minus dot omega. Yeah? Euler's formula. Remember Euler's formula? Cosine alpha can be written as a power j alpha plus a power minus j alpha divided by half. Familiar? J is square root for minus 1. 1 equals to 1I equals to square root of minus 1. If I apply Euler's formula, I will be able to rewrite my spectral function as O max by half minus infinity to infinity f power j omega plus phi 0 plus f power minus j omega plus phi 0 multiplied by a power minus dot omega and this time. Now one trick can be done. See, if we have something in space of time, it has corresponding something in the space of frequency. Laplacian transform. Everything what it has original in time has its image in space of frequency. If we have delta function in time space, we can assume what same thing exists in frequency space. One divided by double p from minus infinity to infinity a power omega x dx. It's an absolutely thin spectral line. Why do we need it? We will. it appears quite complicated. What mean? Absolutely thin spectral line. It is an absolute. Remember idea of spectrum, optical. Right. Some remember this thing from your school physics? See, yeah, spectrum. Yeah? On this side should be light source, prism, and on the opposite side you can observe different light. If it has some minerals, for example, and I don't know, usually it's natrium or hydrogen, you see, or neon, you see nice spectral lines. Same thing with voltage or current or something like this. We can analyze them in frequency space. If we have ideal voltage with only one frequency in it, what we will see in its spectrum? Yes, infinite thin spectral line. It should be. So, spectral function of my voltage will be P O max. Here will be to F power J V0 multiplied by delta function omega minus omega 0 plus F power J V0 multiplied by delta function omega plus omega 0. Why two elements? Frequency omega 0 minus omega 0, because when you speak on Fourier transform in complex form, you will get spectrum as a pair of conjugated, how to say, elements. I need to add one more element to this picture. If you observe pulse sequence, yes, infinity to infinity, that was m tau. It's a sequence of repeating pulse. This one is repetition period is T capital, and M here is a simple integer. Sequence of pulses. What nearest example of sequence of pulse? PWM operation or inverter operation, or inverter output. Sequence of pulse. You can write it in this way. Double P repetition period. Sum k starts from minus infinity to infinity. Spectral function of your pulse. It's this one is a Fourier transform from one pulse. Repeated at frequencies k double p divided by period and multiplied by delta function omega plus k double p spectrum of pulse sequence is kind of it's a perfect set of lines. Okay, now we knew something about delta functions. Now, let's go a bit forward. Let's go a bit forward. And what forward? Let's say we need to understand limitation in time. Oh, now what we know? What we know? What if we have absolutely fast ADC, we will have no distortion. It's fine. But there is a huge if. If we have absolutely fast. And what if not absolutely fast? To understand what happens if not absolutely fast, general idea, remember, did I show everything? Did we show everything? Idea of, okay, I will see my problem. I don't have space. Okay, next time I hope I will be able to free some space to show everything in life. There is a problem. If your device isn't fast enough, you see distortions of signal numeric in its numeric representation. First, and first correct assumption came from Nyquist. Nyquist said what? If you have, if you deal with signal where frequencies are from starting till max, kind of omega max, to achieve correct representation in numeric form, your frequency of sampling should be at least twice signal maximum frequency. Why? What's the idea? Simple. If you can represent your signal with Fourier role, you will have at least 2 measurements per period for higher of harmonics. For your top harmonic, you will have at least 2 measurements per period. But to understand it exactly, to get strong definition, we need to go from one, not from not general approach, but one specific idea. There was one scholar, Katelnikov, who tried Fourier rules, but on special form. Usually, what's a base for Fourier rule? Sine, cosine, yeah? Remember Fourier rules? Not Fourier series. Sine, cosine. Kotelnikov's attempted to use system sine kx divided by kx. This also is such a system with different k, also yields orthogonal system and can be used as a base for Fourier series. So Kotelnikov attempted to understand what happens. So if my signal is limited with some omega max, Fourier, this form of Fourier transform is feasible. Okay, let's write. So I have some signal what can be represented for which Fourier, classical Fourier transform is possible. So I can represent it with its Fourier spectral function f of omega prime d omega. If I deal with limited spectrum, okay, this signal has a spectral function. F of omega times the time. It's a classic form, known form of Fourier transform for non-periodic signal, or integral Fourier transform. What was named in your class? Integral Fourier transform. So here it is, integral Fourier transform. It exists. It is possible, but what we will see? If my signal is in limited frequency range, its spectral function will be 0 for frequencies below minus omega maximum, not 0 something minus omega maximum, and again 0 if frequency is greater than omega maximum. My signal is within limited frequency range. Trick can be done. Here for I don't know, something like this. Magnitude of spectral function. Here omega maximum. Here it goes minus omega. It's how to say property of integral Fourier transform. You get conjugated values. Spectral function for minus frequency is a conjugation of spectral function of frequency. That's why they are symmetrical. What? Symmetrical. Oh, symmetrical. What can be done? This can be, since it's a function, we can apply Fourier transform on it. Fourier transform on result of Fourier transform, which pairs double omega. It's what? In pure mass, in abstract mass, we can assume what this is one period of some kind of function and perform a Fourier transform on it. it's a strange trick, but it can be done. So we will get something like this. 1/2 set of Fourier weights or Fourier factors f power j double p divided by omega maximum double omega maximum omega. I will get the result of Fourier transform as some, what do I mean? This thing, already representation in frequency space, can be assumed as a sum of kind of Fourier series with these factors. Fourier representation or integral result of integral Fourier transform, I can assume that it can be substituted with normal Fourier rule. Typical Fourier transform Fourier series factors will be 1 divided by omega maximum integrate minus omega maximum to omega maximum spectral function of my signal as a function of frequency at power minus k p divided by omega maximum frequency d frequency can be a bit simplified as not important. Can remain like this. If you compare with Fourier rule, we can understand what each is double p divided by omega maximum signal values at points minus k p divided by omega maximum, or double signal values at minus when, or maybe I will wait 1 second. I will confuse. Let it be delta time minus delta time. So here this time space is p divided by omega max. I will explain why I start Rax discretization time. Okay, let it be delta t. I will go. I will correct it. rectify it. While start and stop. So, spectral function can be rewritten as delta sum k starts from minus infinity to infinity is from minus delta time f power your k delta time and here also at omega equals to delta time sine starts from minus infinity to infinity as from k delta time f power your k delta time omega. If we now use this representation of spectral function we can write our signal. One moment, I will write our signal. My signal can be written 1 divided by double P minus omega maximum omega maximum delta the sum by k signal from k delta time multiplied by a power minus your delta time a power your omega time and it will be equals to second, but it will be equal. It's equals to something k starts from minus infinity. It's infinity. Here delta divided by double p. Here will be signal taken at delta sum because of my signal f power not omega t minus delta time t omega. In case of this sine x divided by x rho, we can write our signal as sum k starts from minus infinity to infinity signal at values k delta samples of signal sine omega maximum t minus delta divided by omega maximum t minus delta. Here is signal representation as a Kotelnikov series. It's a Fourier series, but on base not sine cosine, but sine kx divided by kx. Kotelnikov series is a Fourier series but on base of sine kx divided by kx. On different base of signals. Something like maybe Котельниковская. Котельниковская equals to, in our case, sine omega maximum t minus k delta t divided by omega max t minus k delta t. If we look on this Kotelnikov base function, we'll see what we can see one moment. What equals to 1 when time equals to k double p divided by omega max. And it's equals to 0 at a moment m, which is integer 1 divided by double. Okay, here will be omega max and here will be double p. M here is an integer. So, at the time point pk equals to k double p divided by double omega max, or k1 divided by double f max, in whole Kotelnikov rule only one will remain, only one element, one member, and its member equals to value of signal at point pk. But since this rule represents signal precisely, any time moment, what does this mean? What? This means, what if my signal is limited by f max, do not contain any components higher than f max, it can be fully represented if we take time steps p divided by omega maximum, or 1 divided by double f max. Fully represented. That means, what if we have signal with frequencies up to omega max, sampling time should be greater or equal p divided by omega max. With this strange trail, I achieved confirmation of Nyquist idea. If I need to represent my signal precisely, sampling frequency should not be less than double f max. I started with blah blah blah, all its idea. Here is proof. Until your sampling rate is lower than double max frequency of your signal, result will be failure. Here is proof. Since it's true for sine kx by x, it's true for all Fourier series. Okay, so next time I'll need to show limitations on discrete time Fourier transform. It's important for us. It's our specific thing for our business. Now we see I prove limitation in frequency, but this is not all. In our case, there is a serious underwater potential problem. Serious problem we can hit. In our signal processing. At first we have idea. Now Nyquist frequency is not blah blah blah, but it's proven. And what's important, why I need to prove? Nyquist frequency sets a, benchmark for my analog path. I need to pre-process my signal before I can do anything numerically. What I need? I need to cut off all frequencies above this, what I just wrote, double frequency of sampling. And better do it without distortions. It's a benchmark for my analog preprocessing. And next point, I need to convert set of samples into something I can something what I can work, I can apply my mass to. To do so, I need next lecture. Okay, now maybe some questions, maybe online some questions. Who would like to ask? They still pass up my claims. Let's see what we have. Come on, FPS. Why it's so slow? We have irits. No. Izdifferents rīkojums ir pāvēlē. Kaut kas, ko jāizpilda. Jāsaka jāvoļ un jāizpilda. A nosacījums ir nosacījums. Ja kaut kas, tad kaut ko. Ir tāda lieta saistoši nosacījumi. Saistoši nosacījumi. Teiksim, nedrīkst mest atkritumus uz ielu. vai jums jāsaka ar to savu teritoriju un tā tālāk. Tas kaut kas ilgstošs, saistoši nosacījumi. Rīgas doma var izsniegt saistošs nosacījums, ka jums jānokārto savu teritoriju, ka nedrīkst būt sniegam. Tā, since I don't see any questions